Hello everyone. Welcome to this presentation titled Optimizing for Humans, Nim Metaprogramming for Zero-Cost Abstraction on Microcontrollers. My name is Peter Munch-Ellingsen. Over there you have my GitHub handle and IRC name, along with my website where I write about Nim programming and other kinds of programming. But what do I mean when I say optimizing for humans? Most programming languages try to optimize the way that we as programmers interact with our computers, how we tell them what to do, and how we are able to read and maintain the code that we write, so that we need to understand the code, but also the computer needs to understand the code. On the very left-hand side here, we have some assembly code, which is just taken from some assignment I did in university. And this is really sort of the lowest useful level of abstraction. We have some labels, we have names for the registers, and we have some like names for the things we can do, like jump, equals, and move stuff around. This is just sort of the step above writing binaries by hand, which would just be all numbers, which wouldn't be pleasant. But it's really not doing much more than just translating stuff. On the right hand, we have some C code, which has sort of stepped away from the cache registers and like direct CPU instructions over into sort of more memory manipulation. We have pointers, we have loops, we have types, although not very strict type system. We also have like calling conventions for functions, which may or may not be optimal for what we want to do, but it allows us to sort of structure our programs in a way that is probably for most of us easier to understand than assembly code. Then we have languages like Clojure on the left there, which is a functional programming language. And functional programming languages, for those who don't know, don't allow you to modify data. That's sort of their whole, or part of their regime. And this means that they have put a lot of work into making super optimal data structures that allow us to do what looks to us like copying, but under the hood it shares the memory and it does some clever tricks and stuff, so that it's optimizing the computer part, but also giving us the functional paradigm, which at least I find pretty easy to work with. However, it ends up with doing more work, more copying, than what you would find in a typical imperative language. On the right here is Nim. It looks kind of like Python, but it's, we'll get into that more later, but it looks kind of like Python. We have stepped sort of, it's sort of in the same like imperative language. It looks kind of like Python, looks kind of like C, but we have metaprogramming capabilities and we have a much stricter type system and a lot of other good features that sort of take it one level up in the abstraction over C. So when I'm talking about microcontrollers and small targets, another language which a lot of people are using is Python. You have Python and JavaScript and these interpreted languages. And they are fine for our computers, which are super powerful compared to these things. But we still use a lot of these smaller targets, especially now that IoT and home automation, stuff like that is coming in. On the very left here, we have an Atney85. It has 6 kilobytes, I believe, of program memory, 2 of which is used by the bootloader. So we have 4 kilobytes of programmable memory. In the middle, we have an Arduboy, which is based on the Arduino Leonardo. I believe it has 32 kilobytes of programmable memory, tiny black and white screen, a couple of buttons, and that's pretty much it. On the right hand, we have an ESP8266 on a breakout. And it has 4 megabytes of programmable memory and like a Wi-Fi antenna, and like it's a whole another ball game from the other two, but it's still a pretty small target. Put into comparison, it has 4 megabytes of programmable memory. That is the size of our program, like the disk space. That is half of what the machine I'm recording this on has L3 cache in the CPU. It has, I believe it is 32K-ish of RAM, or 40K of RAM, I think, after stuff is used for some other things. 40K that we can use. Which is about what this machine has per thread in its L2 cache. So as you can see, these are super small targets compared to our normal computers. I mentioned Python in the last slide. And just to get sort of, so Python is used by a lot of people. It is sort of easy to type, or touts itself as being easy to type and easy to work with, which is what we're trying to do here, right? So I set up a small benchmark, ran it on the ESP8266, and the only reason I ran it on this chip, it has a lot of overhead with the Wi-Fi and stuff, is because it was the only chip I had that was actually big enough to run Python or MicroPython. As you can see here, we have iterations per second, and we have flash memory footprint. So iterations per second is just some simple, stupid payload in a loop. Time how many times it is able to run that for a second. You can see C++ and Nim here is in the sort of 3,500 iterations per second. MicroPython is sort of chilling at 45,000. But despite of that, the flash memory footprint of MicroPython is way up there at 640 kilobytes. These Nim and C++ is in the 230 kilobyte range, which is mostly all of the stuff for the ESP8266, the Wi-Fi stuff, the like the runtime for it, all of that. I compiled the same benchmark on an Arduino Duo Melanova, and it took 960 bytes or something like that. So this is pretty much just overhead for the ESP8266. But it shows us how big sort of Python is on top of this, and how poor the performance is compared to something native like C++ or Nim. In these graphs, Nim outperforms C++ in both flash memory footprint and iterations per second. That is probably just my compilation and like how I ran these tests. I wouldn't look too much into that. They are basically on par in performance and size. But yeah, what is Nim? For those of you who haven't heard of Nim, Nim is a compiled language. It compiles via C or C++ for these kinds of targets. It also can compile to JavaScript if you want to run web stuff, but that wouldn't work on a microcontroller. It is statically typed. It might not look like that from this example because it also has implicit types. So it sees that these are zeros, that's a number, lines, that's strings, so it knows that line here is a string. And the type system is a lot more strict than C or C++, but we also have like generic types and a lot of stuff like that. So you can really leverage the type system to our benefit. I included a quote here: "The speed of C, ease of Python, flexibility of Perl," which I originally thought was something that Andreas, the creator of Nim, had said. But he told me afterwards that he hadn't said it, and I have included it in other talks, and now it's been attributed to me. But it is true. It really combines sort of the best of different things. It's super easy to write, as you can see. It has the speed of C, as we saw in the last slide, the size of C, compiles down to single binaries on computers. And as we will see with the metaprogramming stuff, it's a really flexible language. It also has a controllable garbage collector. Last time I was at FOSDEM, I said that we couldn't run the garbage collector on microcontrollers. That was a year ago, and I'm happy to announce that now we can run the automatic reference counting sort of garbage collector on these targets as well. So now we have the full standard library. We can use all of Nims features. Whether we want to or not, that's a different question. We don't have a lot of RAM on these devices, but the overhead of the automatic reference counting is really low. And if you don't use any garbage collected types, it's 0. So it's never been easier to program microcontrollers in Nim. Just a quick word, if you use it for computers, you can turn the garbage collector off, you can control how long it runs. If you're doing games in it, you can lock the frame rate and do garbage collection for the rest of the time in your frames, stuff like that. It's super flexible. So don't be scared away by the garbage collector, like I almost was when I first discovered Nim. But Nim's really killer feature is the metaprogramming, which is what I'm here to talk about today. This is just a simple example. So macros look like functions. This one returns untyped, which is an abstract syntax tree. It takes in a string, with a static string, that is a string that is known on compile time. And it does this splitting on compile time, and it creates a bracket, which is square brackets with just literals in it. So the toLookup call here will just create an array of string literals. So it will convert that data, and data is defined as a const. Const are compile time only. So opcodes here will, like that string will never enter the binary. Only the things that we use from this opcodes thing will actually enter into our binary, which is pretty cool. I mentioned that Nim macros are AST based. On the left here, we have just some simple Nim code. If we pass that into a macro, we get a syntax tree, something like this. So if you've written macros in C or C++, those are text-based. You get something in, you just do simple substitutions, and you pass it back. In Nim, this is done with a syntax tree. So you could grab nodes from a tree, you can put nodes into other parts of the tree, you can write your tree from scratch based on something else. And this is an untyped tree, so you see we have identifiers, identifier X and identifier for echo. If it was a typed tree, Nim would have already verified the types of everything, checked that the functions existed, and we would be able to see that X here is an integer. We would be able to see echo and the signature of echo, and we could do stuff based on that. So Nim is really, writing macros in Nim is much more pleasant than writing macros in C or C++, and we write them in Nim code. The macros in Nim evaluate Nim code in a virtual machine. So we type macros and our code in the same language, which makes it much easier to do than many other languages that have macro or templating systems. So a lot of what I'm going to talk about today is based on a project I did for a game jam for the Arduboy. It's a very simple little game. We have a level. Those mountains there are parallaxing in the background, so moving at different speeds. This is a character drawn of multiple sprites. We have particle effects, both when he picks up the pickups, but also when he runs on the ground. You can change between different characters. And on the actual device, it will actually blink parts of the or different sprites at different ratios to make 3 levels of grayscale. And it also tracks your score and stores that in program, or stores that in the memory of the device, so it survives a reboot. And all of this, the code for this is about like 400 or 500 lines long. It's all also available on my GitHub. But it really shows like how easy we can do a lot of stuff in Nim. So what allowed me to do this? One thing where I started out with sprites. Every game has to draw sprites onto the screen. The way you would typically do this in an Arduboy game is that you would either go to a website, upload your images, you would get header files back, import those into your project, and they will contain an array of data that goes into your program. The other way is to download this program. You can put it in a make file, for example. You had to, of course, install that. That is now a dependency, a compile time dependency of your project. And the make file, you need to, if you want to add another sprite, you need to put that into your make file, so on and so forth. In Nim, I wrote this. So I have taken out a lot of the actual functionality here, but it reads BMP files. So this load BMP, that is reading monochrome BMP files from our disk when we compile, and then converts those into the same kind of array. And I'm using under the hood the C++ drawing functions. So it converts it to the same kind of array. It puts that in progmem just the same way as we would with a normal thing or a normal sprite. But what is even more interesting is if you look at my type definition here, I have a count, that is the amount of bytes, and you can see that represented here in my array type, and also down here. But you also see I have width and height, and those are all static integers, but I don't use them in my type definition. So where do they go? They are now creating a new generic, or they're creating a version of the generic sprite type, which has width and height coded into the type. So in my Nim code, I can now, on compile time, see how big my images are, and I can expand my function calls to draw sprites with this information. But they will never enter the program memory unless my code, unless I use them, and unless I want them there. So this is what my drawing code in the actual game looks like. We have the sprite path that is now a string define. So that is, we can pass that as a compiler flag. Just define where all my sprites are. I just call load sprite with the name I want to load it into, and the different BMPs. And it will just read the BMPs from disk. If I edit them, I'll just read them in again. In the make file, I would have to make sure that the make file's matched. Also note that when I'm calling this draw sprite, the calculate player bounds is just a small template that expands X, Y, and like calculates that based on where in the game I am. So that's just to get the position of the head and the body and stuff. But here you can see I draw these sprites. I just give them the sprite and the X and the Y position. And if we look at what this does under the hood, we have, so these are called draw bitmap. They're similar, but they're, yeah. Just look at them as the same. So I call this with XY, which are 16-bit integers, and my sprite, which has count, width, and height coded into the generic type. And then I use width and height here. And this is just the C++ call. So as you can see, it takes a pointer to some data. In C++, I could give it any pointer. And if that happened to not be a sprite, I would just draw garbage on the screen. But in Nim, I now know that this can only take sprites. So I know I can't mess that up. I also don't have to keep track of my width and height anymore, because that's stored in my type. So if I change the dimensions of my sprite, I don't have to update anything on my code. And if I, or depending on how I want to write it, draw it, of course. And if I were doing this in C++, I would have to keep track in my head of the width and height of all my sprites, or I would have to look it up every time I wanted to draw a new sprite. In Nim, I don't even have to know the width and height of my sprites, because Nim reads it in for me, and it uses those values when I need to draw them. No fuss. What is also interesting here is this masking function. So in the same way that I'm occluding things behind myself, but not my background, you can also draw masked things with the artboy. The C++ thing just takes 2 pointers, a width and a height, and it draws them masked. The problem here for us, or the problem here is that if I pass in one pointer to an image of a certain size and another pointer by accident to an image of a different size, that will just give me super weird effects. Here, since they are both, so bitmap and mask are both the same instance of this generic type, I know that their width and height will always match. The Nim compiler will stop me from passing in something wrong here. And we know, like on runtime, these are just the same pointers that we have in C++. There's no overhead in the size or the speed. Everything is just encoded on compile time into a type. We don't have to think about it. So not only is it more ergonomic for us to use, but it has also provided us with some extra safety features, which is really cool, and all at zero cost. When I was done with sprite drawing and sprite loading from BMPs, I decided to reuse my sprite loading logic to load the levels and the position of all pickups. So my levels for this is actually just a GIMP file with layers. One layer for each kind of pickup and one layer for the level itself. And depending on how big that file is, that's how big my level is. And my Nim code will use that. And I don't have to change anything in my code if I want to change the size of my level. And it just uses the same progmem stuff, the same kind of logic with the arrays. This one has a width that isn't encoded in there, just available on compile time. And it also has these super neat procedures. So these are bracket accessors. So I can say like spike number 5 would just be spike brackets 5. In C or C++, I would need to do PGM read byte because these are stored in progmem, so the program memory. So I would need to do program memory read byte or read word in order to read these out and use them in my code. In Nim, I can write these simple accessor functions, which will read these, do this reading for me, and do all of the pointer arithmetic and just read that out. So my code is super clean, and it still just does the same stuff behind the scenes. Another really cool thing, so none of these microcontrollers have built-in floating point in their CPUs. So if we want to use floating point, we would have to build in a software floating point library. Not only is that big in terms of program memory, but it also takes up a lot of CPU cycles to do floating point math on an integer CPU. What I did here was I imported fixed point numbers, which is just a library that someone wrote or Sev specifically wrote in Nim. So I just defined two types, speed and position. One is stored as 8-bit integers, one is stored as 16-bit integers. Both have their floating point at 4, or their fixed point at 4. And I have a particle object that uses these types. And then I can just loop over them like this and add xs is the speed in the x direction. So I can just add that to the particle. I still have this 2-speed that converts a compile time number into a fixed point representation. So the 2-speed 0.1, that float never enters my code, more my runtime code, that is converted on compile time into a fixed point number that represents 0.1 and puts that in my code. So this saves me from having to import a floating point library and or the floating point library that comes with it. And it's just, it looks super clean. It looks like I'm using floating point. I don't have to think about it. It just works really well. Another thing is functional programming. So I didn't use this in Arduboy, but I still wanted to bring an example of this. I mentioned initially that the functional programming languages do a lot of smart things to give us the ability to use sort of the functional paradigm without doing as much copying. In imperative languages like Nim, that is not the case. The data structures there aren't built for functional programming. So when you see functional stuff in an imperative language, typically that involves a lot of copying, a lot of allocations of memory. And in fact, this code will make a new sequence for all of these things. So it will build a new sequence, and then we need to free that afterwards. Just a lot of extra work and a lot of extra memory used. I imported a library called Zero Functional, and Zero Functional isn't written specifically for microcontrollers. It's just a Nim library like any other Nim library. And what it does is that it reads this on compile time and converts it into imperative code. So what that means is that the output of this looks pretty much like how you would do it if you were to do it yourself in imperative code. That means that this has zero overhead in terms of creating these extra sequences. It's just one loop through everything and does all of the iteration, or all of this stuff is in the same loop. And actually when I compiled these two, so I compiled one and then like commented out the other one. And this one here took about, I think it was 800 extra bytes of programming memory. And it has a lot more allocations and a lot more freeing that has to be done on runtime. So I really just want to show this as sort of without, like, there is really zero cost, both to readability to us, but also massive performance gains to be had by using these zero cost abstractions. But yeah, that was all I had for you today. In my talk, Optimizing for Humans. You can find me still on my website and my IRC handle. If you want to learn more about Nim, I hopefully whet your appetite a bit. You can find us on nim-lion.org, or you can join the IRC channel, #Nim on Freenode, or the Gitter and Discord rooms, which are all linked together, so we'll all be talking to the same people, or of course the official forums. But that was all I had for today. I hope you enjoyed the talk, and thank you for your attention.